Okay. Okay, so now we're talking about. Uh, yep. Ha. So, plane polarization. Um, this is all new to me for the most part. I do know plane polarization is like, well, you have waves and they're gonna move in like two ways. So if you're going this way, so it's gonna go like either like this or like this, right? You have two ways the waves can travel, left to right, or up to down, right? So you could say across the y-axis or across the x-axis. That could be one way of thinking about it. Regarding, so with that information, um, what can you do to the waves that falls under plane polarization? So next big topic here, and everything kind of falls under this. So we see that, as we said, they can oscillate only in one plane, either the x-plane or the y-plane, or the vertical plane and the horizontal plane, whatever you want to talk about. Just going to be horizontal, just going to be vertical. And only transverse waves can be polarized, because transverse waves are the waves which, the energy with the particles travel with energy travel, are parallel. So something something like that, right? Um, Wait, hold on. The ChatGPT time. The basic difference between transverse and the other type of wave. Transverse and longitudinal. I know my physics. Particles of the medium move perpendicular, and longitudinal the particles move parallel. The particles of the medium move parallel. So yeah, perpendicular is what we need, because again we'll have the diagram, but if we have this, and it's going like, let's say we just drew this cylinder, so it's easier to understand. So this is the cylinder. So that means if we have particles that are moving perpendicular, so we can go like this, or we can go like this. So from the same point, it's going to be a peak. Okay, so we can go like this. Perspective drawing classes come into play. Okay, so we're seeing it oscillate this way and oscillate this way, oscillating this way and oscillating this way. Well, in this case, it's only oscillating one way. If we drew it in, like, let's say a blue marker, and we drew the other side, so it's oscillating both ways now. Or it could oscillate in either one or the second way. So that's why we're talking about this. If we talked about a wave, let's say we drew the same thing, okay, and we drew it instead in ways that it was parallel. If it was parallel, that means all the particles, they're moving like this, like left to right, like they're just going and they're going, traveling in that direction. Now it doesn't matter because it will always travel in this direction. That's the end goal. So it's not like it'll ever go a different way and then go that way. They can only travel in one way. And that's why we were only talking about transverse waves here, not longitudinal. Because when we talk about longitudinal, when we talk about, what is that? Is that like a marker? That is so cool. When we talk about transverse, and we're talking about going perpendicular, there's actually two ways of going perpendicular, because there's two planes in 3D. Oh well, there's two planes in 2D if we're looking at it like this, and the particle can move up, down, left, right. So there's two planes that can go. Okay. No, because the third plane is actually just the direction of the particle, like is the direction of the wave itself. If it was moving in the third plane, then we would be talking about a longitudinal wave, technically, because it's moving parallel to the wave itself. Okay, now below is the diagram. Finally, we can actually talk about the diagram. It shows the effect of vertically polarized and horizontally polarized. So, see, polarized means that, you know, a normal wave oscillates in two planes, and a normal wave or a polarized wave oscillates in one plane. Okay, so if you have a normal particle, it's going both ways, but when you have a polarized particle, it's only going one way. Okay, these are polarized, so they can only move in one plane, and it's only these transverse waves which can be polarized because those have the two ways of traveling. So over here we have a vertically and a horizontally polarized, and there's two things to know. One is that the waves are passing through a block with the vertical slits which act as a vertically polarizing filter. So the block here is a vertically polarizing filter, so that means only vertically polarized waves can pass through. If it is not a vertically polarized, that means it is going to be just cancelled, okay, or it just won't pass through. So we have a vertically polarized already. This is a vertically polarized wave, and this is a horizontally polarized wave. So if we're going in vertically polarized, and this is a vertically polarized filter, that means it'll pass through, as it says here, without a problem. But the horizontally polarized wave cannot pass through the filter as it blocks waves which are not in the vertical plane. It's pretty easy to understand. It's like a filter. Now, a use of this, right, or its function, as we always talk about in biology, function. So we talk about the properties here, how it kind of works. Now we talk about the function of it. An application of this is polarized sunglasses. They reduce glare by blocking the partially polarized light, which reflects from water and tarmac, as it only allows oscillations in the plane of the filter to pass through, making it easier to see. What does that mean? What that means is what this means is in day-to-day life, you're going to have polarized, like these two are both polarized, you're going to have polarized light or partially polarized light reflecting from different surfaces. In this case, from water and tarmac, right? Now, what we do is we wear sunglasses which have filters on it, and these filters block the partially polarized light because they only allow oscillations of the plane of the filter to pass through. And if the plane of the filter is not the same, the plane of the filter and the polarized filter, the plane of the filter and the partially polarized light are not on the same plane, so it blocks the partially polarized light, making it easier to see. Now we have more of the theory behind this. So you have diffraction in Huygens construction. This is talking about diffraction. I think, why are we talking about this here? Because we're not supposed to be talking about diffraction here. Well, I don't think. Oh, hell no. Hold on. Yeah. I'm not seeing anything here for diffraction, so we are going to skip this part. But it does talk about intensity a little bit, so if you do scroll up a little bit, because we are going above stuff that we did before. This is the intensity of radiation. And it's simply just a formula, that's all they give here. Of course, the theory behind what's used is going to be different. Is there like photon energy intensity? not that I can see. Anyways, what else? Who cares? So that's going to be your polarized light. That's done, right? Just know polarized light can only travel on one plane, and that plane can be blocked with a filter, right? And so it's used in sunglasses to block partially polarized light from, like, that's reflecting out of stuff like water. And yeah, protects your eyes. Now you're gonna have some diffraction stuff. Oh, we learned diffraction before. There's also electron diffraction, which is going to be the important part. So that's going to be the first thing that we talk about, and then we're going to be talking about the wave model and stuff. So let's talk about electron diffraction, right? So you need to have some kind of basic understanding of what normal diffraction is before you start electron diffraction, and this is just assuming that you do have it, which I think I have it, not for the greatest part. Like, I know what this formula is. Where's my cursor? I know what this formula is. I surely know what the formula for D is. D is equals to 1 over n, I hope. So yeah. Hoping that you know what that stuff is, this is going to be the next big topic. Electron diffraction, as it's the evidence of important stuff, the wave nature of electrons. So we're learning about the waves of light, or just transverse waves in general. And it might not seem like it, but electrons can also function in waves, not just particles. And to prove this, if we want to say that it functions as both waves and both particles, then we need to be using electron diffraction as the proof. Okay. So again, just to reiterate, wave nature of electrons, it's not just particle nature but also wave nature. We can prove this by using electron diffraction. First, let's explain what is electron diffraction. Well, electron diffraction is performed using an electron gun, okay, where you shoot an electron through a vacuum towards a crystal lattice, where then they interact with the small gaps between the atoms and they form an interference pattern on the fluorescent screen. So with light particles are your whatever it was called, your multi-fluorescent, or what was it, like polychromatic light, right? If you have your polychromatic light and it's going through a grating, in this case electrons are so small, so what is the grating going to be for electrons, right? And that's going to be your gaps between atoms. That's going to be your grating for those. Okay, so when you're having electrons moving through great acceleration and they're going towards a crystal lattice where they interact with the small gaps between the atoms, so this is going to be acting as your lattice, okay? And that's going to form an interference pattern on your screen behind the crystal. Now, note that they did mention that it's a fluorescent screen. I'm not sure why, but this is something that you should probably take note of. It's a fluorescent screen behind the crystal. Okay, so there's the cool part, I think, is electrons are so small that you have to use gaps between atoms as your grating. I don't know why I wrote lattice, but this is going to be your grating. Okay, that's going to be your grating in this case, and the pattern that you'll see, the interference pattern, looks like what they mention, concentric rings. Okay, so this apparently to people looks like concentric rings. So that's what it's going to be, where I guess this is going to be your most intense part, and as you go out it gets thinner and thinner and thinner. So you go back, and the gaps become gaps here are larger, so I'm not sure what's going on here, but there are more gaps. There are a higher number of gaps. Now, if electrons only had particle nature, then you would expect that it looks like one giant point, or one point, where the electron beam has passed through the lattice. However, this is not the case, as electrons undergo diffraction, something that only waves can experience. So, first of all, what would particle nature look like if we drew another box and we drew particle nature going through this grating, aka the crystal lattice? It would look like this. Just this. Because we're shooting particles, and particles are just going and hitting this one point. It'll find a way through the lattice, right? Like the electrons are coming in, find a way through the lattice, and they'll just travel and hit this. And after hit it, it'll be one big spot on the screen. However, it's not. It's a weird, it's big in the center and it's going out and it's becoming less and less apparent, which is similar to when you see waves undergoing diffraction. So now what we're seeing is electrons undergoing diffraction, aka something that only waves can experience. So this means that this is wave. So this is a proof or evidence of the wave nature of electrons, because we see electrons undergoing diffraction, where waves is the only thing that can experience diffraction. So electrons can be waves. Okay, so that's gonna be your proof. Okay. Particles, if it was a particle, it would be a single point, as mentioned here. If it was a particle, it would have been a single point, but it forms concentric rings, which means that electrons are undergoing diffraction, which means that electrons can be waves, because waves can only experience diffraction. Okay, simple as that. Simple as that. Okay, now de Broglie relation. So this is going to be the formula or the theory behind it. Again, this was kind of more of like the practical, like how we sometimes do this. This is the practical part. This is the theory part. Okay, so this is the boring part. Okay. So the de Broglie, very beautiful name, states that dude named de Broglie stated that all particles have a wave nature and particle nature. And the wave of any particle can be found, wavelength rather, using the following equation. So wavelength equals to h, which is Planck's constant, divided by p, which is the momentum. Now we're talking about momentum of a particle. That's why it's p. But I know it's funny to use momentum of a particle. However, we are using an electron gun, which means we can calculate at what rate, or at what rate is the proper word. What rate is this electron being shot at? What is the momentum of that particle? So yes, lambda equals to Planck's constant over p. Now, before we talk about more about the thing, let's talk about more about the wave nature. Let's talk about waves' behavior at a surface, or at an interface rather. So there's two types of surfaces, right? There's the one where it passes through, or one where it reflects off of. So, which means that we can quantify them. So you have an interface, the boundary between two materials. So this is N1, this is N1, N2, N2. You have two different types of behaviors at the interface. Okay. So this is an interface is going to be your point where they meet, or the boundary. So at an interface, waves can either be transmitted, where they pass into the next material, so they go into the interface. Yeah. Experience refraction is possible if they have different refractive indices, okay, or indices, whatever. Now you have reflection, when the waves bounce off the interface without passing on into the next material. Okay. So absolutely not. Zit tight. It cannot pass into the next material. It needs to bounce at the interface, aka your sin I needs to equal to your sin R. Your sin R not being refraction, but being reflection. Okay. There, it's not passing into, but over here it's passing into the interface. Past the interface. Interface is just the boundary. Remember that. If this line is the normal, then this line is the interface. Okay. You have medium 1, medium 2, that's going to be on one end. So now, you have two techniques, or well, you have one technique. Pulse echo technique. What is this? Well, it is used with ultrasound waves. Now, ultrasound waves are just waves with a frequency greater than 20 kilohertz. So you can just imagine them as normal transverse waves, just with a very high frequency. So high that we can't hear it. Now, this technique, specific technique, is used for the imaging of objects. So we're already having application here, or as we like to say it in bio, your function property was given here. You have your two, your two ways of your waves interacting with the interface. But now, with that information, what is the function? What's the point of learning this? What's the function? So, when you have ultrasound waves, we can use this technique for the imaging of objects, notably medical imaging. This technique relies on the fact that waves are going to be reflected when they meet boundaries with different materials. So, we are already stating that waves are ultrasound waves in this sense. Ultrasound waves are reflected when they meet boundaries between different materials. Okay, so here's a little practical description of it. A few steps. We'll talk about that. But again, just need to reiterate this. We know that waves can either reflect or transmit, and in this case, we know that the waves are reflecting when they meet boundaries, or when they, hit the interface between two different materials. I don't know why they use boundaries in this, but if they say boundaries, it's boundaries. But know that boundaries can be used interchangeably with the word interface. Okay. Now, short description, the practical description. We're going to have 4 steps, and then we can talk about the wave model and photon model of electromagnetic radiation, which is going to be pretty cool. So, you have your ultrasound waves, like a source of your ultrasound waves, and it shoots a short pulse into the target. And note the word transmitted, that means it passes into. Okay, so if you have the body, okay, so you like the pants. Okay, so if we had a dude, he's chill, right? We are shooting ultrasound waves into his body. Okay, so we have the little biddle, okay, perspective, and we're shooting an ultrasound wave towards his body, and guess what? By who would have guessed? It's transmitted into his body. Okay, so it goes inside. Now, let's get a close-up view of what's going on in his body. So this is the entrance of his body, and that's his body. Okay, this is his body. Okay, and this is the air. Now, as we're seeing the particles enter, what happens? So it enters and it travels inside the body until it reaches 2 mediums where the pulse is reflected back. So it reaches a boundary between 2 mediums. So bam, we see another medium over here. This is going to be, let's say, his intestine. Okay, this is intestine, super crazy intestine. It's going to hit this intestine, and guess what? It doesn't like to, it's not going to interfere with that. I mean, it's not going to, transmit into that. It's not feeling good. It's going to just go back. We are out of here. We are leaving. Okay? We are leaving. So, we're going from entering to leaving, entering, and then get the hell out of here. We're getting out of here. Okay? So, it's reflected back. Now, what's variable in the sense? How much it reflects can be variable, and it depends on the densities of the materials. That makes sense. Your N1s, right? How much? Well, it doesn't necessarily make sense, but it can make sense, right? If refraction can be changed by the density of the material, then I say then so can the reflection, right? I feel like that correlates. So it states already that the greater the difference, greater the reflection, which means that if you're having, you know, well, they're saying the difference in densities of the materials. So what materials are we talking about here? Are we talking about, because so far we've actually seen three materials. We're seeing air, body, and intestine. Well, since we're traveling only within the body and within the air, those are the two um, those are the two mediums that we're traveling inside of. We are only reflecting off of intestine. We're not traveling inside intestine. We're talking about the reflection, amount of reflection within the body, right? That depends on the difference between the density of this and the density of this. Okay. So we're not talking about the density or anything of the intestine, only of the body and air. So just remember, law, greater difference in density, greater the reflection. This I think would make sense to most of you. The reflected waves are detected as they leave the target. So, we've shot some waves into Michael. Now they're coming out, and there's a big screen, so it's detected on the screen, and the screen gives you a little picture. Oh shit, there's a big butt in Michael's body, Oh shit, Michael has a baby. He's pregnant. Oh shit, not great news. Anyways, so they're detected as they leave on a screen, right? And the intensities of the reflected waves are used to determine the structure of the target, and the time taken for these is used to determine the position of the object. So you could perhaps think a soft part, you have more waves that are transmitted inside, but still few particles are left out, very few, but most of the particles are going in. So that can tell you that this part is soft. That tells you the structure, okay? And the time taken, let's say we have we're having it goes like this, right? So if you're having particles, and you're having particles that go in and reflect out, there's like loads of particles here, and it's also reflecting out loads of particles here. Well, these particles are obviously going to reach first, and these are going to reach last or second. Compared to this, it would reach third. So the fact that it's reaching third, the time difference or the time taken for each of these reflected waves to return, it can help you determine the position of the objects using speed equals to distance equals to speed times time. Okay, using this formula straight up just tells you we're using this formula to calculate the position of the boundary, okay, or of the object using the time taken. That's going to be, so you have two variables here. That's going to be your intensities of the waves and the time taken of the waves. So yeah, intensity helps you define the structure. If the particles here was less and the particles here were more, then you can kind of imagine, oh, okay, this part must have been like a more softer tissue. This one was more rigid. This one was more rigid. Okay. So that tells you, oh, okay, this is definitely like the butt crack, and like the inside of the butt is like really soft, right? And it's like these are like super hard, like metal. So like the waves are coming in, No? Alright, my fault. So moving on. Shooting a wave into a baby, let's go. If the duration is too long, they will likely overlap, meaning that the amount of information you obtain will decrease. Right? So basically, we're shooting waves at a rate. We're not really shooting waves like, we shoot them, wait for them to come back. No, that's not really what we're doing. We're just shooting waves at a rate which we think will be enough for them to, come back, and we know that it'll be safe, like it'll be clear, like it hasn't interfered with any other waves, right? But the problem is we don't do that. We do it once at a time, and sometimes if it takes too long, then it'll reflect back by the time another wave is shot, which means that they will interfere, and they'll overlap, they'll interfere, so the resolution of the image will decrease because it's just going to be different. It's not going to be clear enough, clearer. Okay, and the wavelength of the waves the wavelength as the wavelength of the waves used increases, the less fine detail can be resolved, meaning the amount of information will decrease. So we're having two amounts of information that can be changed. That depends on duration of the pulses being too long, or the duration of the pulse. Well, yeah, that's what we meant. And the wavelength. So the duration means it's going to hit another wave, meaning overlap, meaning interference, meaning the resolution of the image will decrease. Wavelength of the image increased. Fine details cannot be resolved. Fine details, less of them can be resolved, or you can't resolve as much details because the wavelength is higher. Basically, what you can think of it as, when you have like super small things and you have like very big objects, when you have a big wave here and you're hitting stuff, you're getting the general gist. So you're kind of getting like, okay, this is big, this is small, this is going bigger and smaller until it just cuts off here. When you have something small and you're shooting a big wave at it, well, it's only going to tell you it's the same size. But when you have a very small wave and it's going towards it, it knows exactly where the bumps happen, all the little fine bits of details. Because the particles are smaller. I mean, it's just going at a smaller wavelength, smaller frequency. It knows. Okay. So we're just gonna say, duration of the pulse increases, overlap increases, resolution or amount of clarity in the image decreases, wavelength increases, fine details that can be seen decreases, resolution decreases. Now we're having wave model, photon model, and of the electromagnetic radiation. So we have the EM spectrum, right? And we have two different models of those particles. We have the wave models and the photon models. Now, the wave model, I think, safe to say that we are used to it. What is the photon model? Well, that's why we're going straight into what the photon model is. Photon model states that EM waves, immediately we're talking about waves, and we're inferring it into the definition of model, of the photon model. We're stating that EM waves that are traveling in discrete packets can be called photons, which have energy directly proportional to their frequency. So first of all, we knew that energy is proportional to frequency. Okay, as the frequency increases, we know that the more energy is stored in their waves. But now the only thing we need to really understand from here is when you have EM waves and they're shot out in little particles, little packets, kind of like computer science, little packets. Each of those are going to be called your photons. So instead of these ones being called packets or bytes or whatever, packets containing little bits of bytes. Now we have packets containing EM waves called photons. Okay. Now on the other hand, in terms of wave model, EM radiation can be described as transverse wave. Oh crap, did I just say something wrong? I guess each packet inside here does not contain a transverse wave. It's just a discrete packet. But it says EM waves traveling in packets. The wave model, EM radiation can be described as a transverse wave. Well, I'm not sure here. Initially, light, which is a type of EM wave, was believed to be composed of tiny particles, as this could explain the refraction and refraction of light. However, light was later proved to act as a wave through diffraction experiments, so believed it was formed of waves. Before long, the discovery of photoelectricity. Before long, due to the discovery of photoelectricity, the attitude towards the composition of light and EM waves changed once again. Light had now been proven to act as both a particle and a wave, which led to the development of the photon model of light and wave particle duality. So it turns out I have been wrong in most of this case. I said that electrons can be wave particle duality, but no, light can be wave particle duality, which, to be honest, is way cooler. Okay. So, yes, light can be reflected and it can be done. Those things can be done to it, which means it's a particle. However, it can also be diffracted, which means it's a wave. So that means it has both properties, and it can have a photon model and it can have a wave model. Now, EM waves, people are, beforehand you might have known that photons are EM waves. You can have, across the entire spectrum, you can have EM waves, just at different frequencies, aka different energies, right? So that's one thing, that's one way to think about it. You can think about the EM waves traveling in packets called photons, or you can just think of the EM waves as a radiation pattern or whatever, as a one big transverse wave. So you can think of it as a continuous wave or discrete packets of waves called photons. I would say that's how I would define it, or that's how I'm understanding it. Now, why are we discussing this? Again, packets called photons, big wave transverse, right? Packets, aka allows it to travel in tiny particles, aka tiny packets, okay? And then also, aka big wave allows it to travel through diffraction or through gratings, creating a diffraction pattern, allowing the dual particle wave particle duality type shit. Now, we mentioned the energy being proportional. Let's talk about it. Photon energy, direct proportion of frequency, HF, we're having Planck constant again, God knows what that is, times F, which is the frequency. Now we said, this wave particle duality type shit, it was discovered due to photoelectricity. How is that? So, what is photoelectricity? Photoelectric effect is where the photoelectrons are emitted from the surface of a metal after light above a certain frequency shown on it. This certain frequency is different for different types of metals and is called the threshold frequency. So, we're saying that photoelectrons, aka the electrons from the metal, these are photoelectrons. These are just electrons, but these are photoelectrons. These are electrons which are emitted from the surface of the metal. It'll be only emitted after light above a certain frequency shown on it. We're not talking about energy, we're talking about light. Light carries the energy depending on the frequency, but that's why it says a certain frequency is shown on it, aka a certain energy is shown on it. Okay? This certain frequency, aka energy, is different for each type of metal. So electrons can be held on to different amounts of strength, and the amount of energy or amount of frequency rather that's used, that is enough to get these electrons emitted out in the form of photoelectrons is called your threshold frequency. Now your photoelectrons are emitted because electrons near the surface of the metal absorb a photon, and therefore they gain enough energy to leave the surface. You can think of it as, ionization energy. It's gaining enough energy to transfer and go up, enough of the quantum shells or quantum levels or energy levels or whatever you want to call them, in order to actually just escape and leave the surface. Now, talking more about your threshold frequency and different things like wave work function and the photoelectric equation itself, Um, Threshold frequency, minimum frequency of light, it needed to emit your photoelectrons. We knew this. And it depends on the type of metal. Your work function is the minimum energy required for the electrons to be emitted. So you can think of it as the threshold frequency kind of equaling to the work function, as long as your threshold frequency's energy in there, in that threshold frequency, is equal to the work function, which is the minimum energy for the electrons to be emitted. Then it can be emitted, right? As long as the threshold frequency, the energy within that threshold frequency, is equal to the work function, which is the work function is the minimum energy. Now, your photoelectric equation shows the relationship between your function, work function, the frequency of light, and the maximum kinetic energy of the emitted photoelectrons. Right now, before we continue, your maximum kinetic energy will be your excess energy is going to be converted into kinetic energy. Okay, let's say you put in energy, and there's more energy than the work function. Then that excess energy will be your kinetic energy. Okay, so E is going to be your photon energy equals to HF, which is going to be your Planck's constant, times your frequency, equals to your work function plus your kinetic energy. So if HF is equals to the work function, then there will be no kinetic energy. However, if your HF is greater than the work function, then there will be kinetic energy. Okay, that's what they're saying. So you have your basic amount of energy that you're inputting into that in each particle in that wave, or each particle in that each photon has this much energy, and you're putting that onto this electron in order to make it remove or emitted. So there's two energies here, the energy that's needed to break this and the energy that you have left. So the energy needed to break this is going to be your work function, aka this thing, and the energy that you have left is going to be your EK, your excess, or your kinetic. So that's going to be it. These are the two things which factor in to produce this. Your electron volt, that sounds sick. So electron volt is, well, this might be a totally new thing, but I don't know. Electron volt is a unit of energy used to describe small energies. Okay. Sorry about that. So electron volt, I suppose it's just voltage but for electrons. So it's a unit of energy, voltage, but for small energies, electrons. 1 eV is equal to the kinetic energy of an electron accelerated across a potential difference of 1 V, or 1.6 times 10 to the power 9 joules. Okay. So it is just telling you straight up that it's going to be this amount of joules. That's the kinetic energy. Okay. 1 eV is going to be this much energy. And what is that energy? Well, that's the energy that is the kinetic energy of the electron that's accelerating across the potential difference of 1. So if you have a circuit and it's going across, and you're putting in 1 eV, something like this, and we're measuring these two distances, and if the potential difference or whatever, you're inputting 1 volt, and the energy of the particles accelerating across this circuit, okay, that's going to be the kinetic energy. There is going to be 1.6 times 10 to the power minus 19 joules. Now you can convert between joules and electron volts quite easily. Joules to electron volts is divide, and electron to joules is multiply. So again, 1 V, and you're having the energy is going to be 1 eV. Over here, when you're putting 1 V, the 1 eV, the energy, 1 eV is just the energy that's used for the small energies, for each particle, for the electron's energy, which is very small. But if you want to talk about it in big boy terms, that's 1.6 times 10 to the power minus 19 for you. Okay. Now the photoelectric effect. Finally, I mean, it might be confusing why we decided to just talk about electron volts randomly in this. I'm honestly not too sure. Hopefully it connects over here. But back to the photoelectric effect. why are we learning about this, right? Because we learned about, two things. We learned about, the proof of, the particle wave duality, that it can act as a particle when it refracts and reflects, aka the photon, and then it also acts as a wave when it diffracts. So, you know, um, well. The reason why it was, yes, okay, diffraction is what caused people to think it was waves, and refraction and reflection caused it was why people thought it was light. But what made people believe that a particle can act as both a particle and a wave, and it's not just one or the other, is is the discovery of photoelectricity. So we learned about photoelectricity, but how does this prove it? So we can use photoelectricity as evidence of the particle nature of EM radiation. So EM radiation, again, when we talked about the electromagnetic waves moving in transverse as transverse waves, right? That's going to be your perpendicular to wave travel. You're going like this, so you're going up, down, perpendicular to wave travel. Wave theory, first of all, a photoelectric effect couldn't be explained by wave theory as, first of all, you need to know what wave theory is, and it suggests that any frequency of light should be able to cause photoelectric emission, as the energy absorbed by each electron will gradually increase with each incoming wave. So it's saying that any frequency will cause photoelectric emission. However, that cannot explain the existence of a threshold frequency. Threshold frequency, I forgot what that is. That's going to be a minimum frequency of light to emit photoelectrons, which is going to be changing depending on your work function, correct? So if it says that any frequency of light can cause photoelectric emission, means that even if you have, a metal with a wave function of, let's say, 100, and you're having, a threshold frequency which produces an amount of energy which does not, let's say it's 80 joules within that frequency. Therefore, you cannot cause photoelectric emission, which means wave theory cannot prove photoelectric effect, okay? Because wave theory states, or suggests rather, that frequency of light, any of it, can cause photoelectric effect. Now, photoelectric effect is immediate, which contradicts wave theory, which suggests time is needed for energy to be supplied to the electrons to reach work function. Minimum energy required for electrons to be emitted from the surface. Okay, this is defining it. So first of all, the second thing that wave theory states or suggests is that time is needed for the energy to be supplied to the electrons to reach its work function. So, electrons has its work function, which is like, let's say it's like a bar, and it fills up. So when the photons reach the electron, okay, and it's like it takes time for energy to go into the electron and the bar to increase, and then finally when it reaches its work function, ding 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 ding, and it goes above it perhaps, then it'll be emitted. Then the electron will be emitted outwards with EK, depending on the excess. Okay? That's not how it works, because in real life we see that photoelectric effect is immediate. That's the third evidence. Now, increasing the intensity of the light does not increase the speed of photoelectric emission, which would be suggested by wave theory, but instead it increases the number of photoelectrons released per second. So intensity of light is literally just how much light you're shooting, just the number of photons you're shooting. And that does not increase the speed of photoelectric emission because it's still immediate. But you will see that it increases the number of photoelectrons that are released per second. So if we have a surface, which is a metal, and we're shooting a light source at it. When we increase the intensity of the light, more light is being shot at this. Which means if it was first, 4 going up 1 second, now there's going to be, 18 that's going up in 1 second. Many more photoelectrons are released per second. Okay? Wave theory would suggest that light does not increase the speed of wave theory suggests that intensity of light would increase the speed of the photoelectric emission, but it doesn't. So you can see between these two things, between 2 and 3, you can see that wave theory kind of suggests that first of all, second point, it takes time for energy to transfer from the photon to the electron, and 3, that time can be reduced by increasing the intensity. So time reduced by intensity increased. Well, in reality, what we're seeing is that it is immediate. It's 1. And the second thing is that intensity, all that increases is the number of photoelectric particles, or electrons rather, photoelectric, or rather photoelectrons emitted per second. Okay, that's going to be your that's what was suggested by wave theory, and that's going to be your real, what's actually happening. The fourth one is that photoelectrons are released with ranges of kinetic energies. Okay, that's going to be a fourth thing. And I suppose that's not there in wave theory. But, whatevs. So, EM radiation. Okay, we're talking about particle nature of EM radiation, which means we're not talking about wave nature, which is what transverse waves would be about. So this point might have been confusing you, but we're not actually talking about transverse waves. Originally, EM radiation can be thought as wave nature with transverse waves, but we're only talking about particle nature in the terms of photons. Okay. Now, photons can have different ranges of energies, can have different frequencies, which is the same thing in wave nature, so I'm not sure what this point is about, but this can prove this is a proving point of why it can be photons, but this is not a disproving point on why it cannot be a wave. Okay. Now we have some more. Photon model of EM radiation. Wait, hold on. Particle nature, and this we're talking about photon model. So we're talking about the photon model, more specific. Not particles anymore. We're talking about specifically the model of the particle, which is the photon, in EM radiation, suggesting that EM waves are released in discrete packets called photons, which have a particle-like interaction and can be used to explain all the points above which wave theory couldn't. So we've already done this. When a photon interacts with an electron, all of its energy is transferred to it. And an electron can only interact with a single photon. So these are all just laws. They're just given you it. Okay? So they're just teaching you each and every single law. So it's telling you, first of all of the energy is being transferred to it, not some, and it's done instantaneously as well, immediately when they interact, leading to immediate emission of the particle. Okay, only one single photon per electron, and if the energy is above the work function, as in if the energy of the wave, if if the threshold frequency's energy is greater than or equal to then of the work function, then the photon electron is emitted. If it's below, it remains in place. Remember, emitted and remains in place is what you need to know. Those are going to be the two results. Is it either 1 or is it either 0? Okay. Energy of the photon is directly proportional to frequency. This is going to be your E equals to HF, again Planck's constant, and your frequency of the wave. The threshold frequency is the frequency at which the photon energy is equal to the work function. So my bad by saying that is the wave, is the EM wave that's emitting these photons, is it threshold frequency or above or below threshold frequency? In other words, is the energy in that wave work function amount of energy and above or less? Intensity, because we already talked about this point and it's pretty easy. Intensity equal to number of photons released per second. Yep, just more particles or more photons, meaning more and more. Sorry, well, okay, this is wrong. Not okay. Well, okay, my bad. This is correct. Just don't understand. Okay, fine, yeah, whatever. So intensity means more photons released per second, which means more photoelectrons emitted per second, because more photons interact with more electrons per second. It's kind of a graded reaction. All electrons will receive the same amount of energy from a photon of light. However, electrons which are deeper in the metal will lose energy through collisions when leaving the metal, therefore will have lower kinetic energy. So if you can visualize this, if we have metal over here and we have particles at the bottom, particles in the medium, particles on the center, particles on the top, if an electron travels all the way on the bottom, hits this, and the work function, I mean if the threshold is the work function exceeds, then it starts coming out. However, it will lose energy as it comes out because it's colliding with other electrons, and as it loses energy through collisions when leaving the metal, then it will have a lower kinetic energy when it leaves. It will have a lower Ke compared to another one which is right here, which just exits straight out and it has a higher Ke. Okay. Oh, we're right there. Let's go. All right. Sweet. Last point. So just before we go on, this is why your EM radiation is can be considered a photon model. So these certain factors that photons can do and waves cannot do. See, we talked about these points right here, but just to further prove them, we've talked about them over here. Okay. We talked about them over here. We mentioned that it takes time, but it's immediate. Waves take time, but it's immediate. Waves have, to decrease the time, to increase the intensity, you have to increase the intensity. But in reality, photoelectric effect, you don't. Why don't you have to? Because of this right here. Because intensity is equal to number of photons released per second, not the amount of energy in each photon, and this will, and anyways, it's already immediate anyways, and so it's not the time that's going to be being changed when you increase the intensity of light, but rather the amount of photon electrons that are coming out. Okay, and remember the last point when we said the range of kinetic energies. Well, see, the point of this was when we have a wave, when we have a photon, or when we have a wave that's being put into here, right, and that's hitting this, if it was a wave, for some reason it would be different, I don't know, but if it was a photon, we're seeing that each electron here has different energies. This is lower, this is higher. Why is that? Because the wave itself has only one kind of it has one set threshold frequency. Has one set threshold frequency with one kind of energy. So why does it have different kinetic energies in each of these particles. That's because when the electron hits a particle that is lower down, if it hits a particle that's, can I use whoa, this is cooler. When the electron, when the energy, when the photon hits an electron that's in a lower area, then what's going to happen is that it's going to collide more and it's going to come out with less energy. That's the only reason. Okay, what was it? And what was the other one? U. One second, chat. Anyways, whatever. So yeah, that explains that. Why can waves not do that? Is something that, well, let's ask ChatGPT. Let's ask ChatGPT. ChatGPT. We're getting a ChatGPT feature. Once again, let's go. So it is said that one of the indications that EM radiation can act as photons is the fact that the photoelectrons have different ranges of kinetic energy as they get emitted. Now I understand the fact that why this can be a proof of EM waves being photons, because they reach they reach the lower excuse my really bad typing, lower level of electrons in the metal, but and so they collide more with the other particles, so they exit the metal, or rather emit, okay, sorry, I don't know what I'm saying, they get emitted with less energy. But how is this a proof of that this cannot happen for waves? Yeah. I wonder, the reason it's being able to compute my answer so quickly, I'm pretty sure it's because it's reading my question as I'm typing it down. That would only make sense. Because if I'm like pausing, giving breaks between my question that I'm writing, it's probably reading my answer. Reading my question is generating an answer while I'm writing it down. Damn, it's still making it. So the key lies here in how energy transfer happens between light and electrons and why wave theory cannot explain it. Now, photon energy is quantized. Einstein's photon theory, discrete particles, yep. Enough energy, yep. Kinetic energy of photoelectron, okay, yeah. That's one. Oh, because it's quantized. Wave energy cannot be quantized. or am I wrong? Sorry, second. Wave theory. Okay, this is just explaining a photoelectric effect? Brother, wave theory, energy of the light would be spread evenly across the wavefront. Electrons would need time to absorb. There would be no dependence on the frequency, light only on its intensity. However, instantaneous electron emission and the fact that there is only one, the fact that only light above a certain frequency can eject. So, in summary, photon theory explains why electrons are emitted with a range of kinetic energies, why higher frequencies of light result in higher and more energetic electrons. Oh, okay. Electron emission happens instantaneously, cannot happen instantaneously, and dependent with the light above threshold frequency and is independent of light intensity. Well, I hope I understood that because I kind of didn't. Just waves can't do it, man. There's, it's spread if evenly, and as a photon, it just has more energy and it's just able to do that kind of stuff. I don't know, dude. Comment it down in the description. That would be pretty cool. This is quite a long video, but this is kind of cool actually. I kind of like doing this. This is fun. So, yeah, only half a paragraph left. It's 12:08. I gotta go sleep soon. So let's do this. So, atomic like spectra, right? So we're talking about the diffraction thing. That's how I interpret it. So you have electrons and atoms. They can only they live in discrete energy levels, right? N1, N2, N3. And if an electron gains enough energy, it can move up in an energy level. So it goes from this one to the next one to the next one to the next one. This is known as excitation. That's true. However, it will quickly return to its original energy level and release the energy gained in the form of a photon of light. So this is an important visualization to make. If you have a nucleus and we have electron shells, okay, if we transfer energy in and the electron is going from 1 to 2 to 3 energy to the third energy level. It's excited by this much, okay? It will at one point quickly return to the original level. Okay, it'll quickly go down and release the energy it gained. So let's say this is Ke, whatever. So all the Ke that it gained to get to the third level, it will release all of that in the form of in the form of something, and it's going to be forming it in the form of a photon of light. Okay, so how we're thinking a photon of light can be used to put in that energy, well, a photon of light is actually is how an electron emits that energy out. Okay, now inside a fluorescent tube, okay, photons are accelerated, causing gas atoms to become excited and then de-excite, releasing photons. By passing, are we talking about the flame test? I think we're talking about the flame test. Releasing photons by passing the light from a fluorescent tube through a diffraction gradient. So now we're talking about, fluorescent tube, and we just have a fluorescent tube, we just have a tube, and we have some gas atoms, okay? Whatever these gas might be, right? If it depends on the element, but if I can put enough energy to make these atoms, the electrons in this gas, excited enough to release a photon, okay? To become excited and then de-excite. It'll release a photon, and that photon will have a frequency, right? As photons do. And so if you want to see what is that color of that frequency, or where would that frequency lie on the EM spectrum, then you get that grating, a prism, and then you get that line spectrum, right? So you get that diffraction, you let that light, you let that photon from that fluorescent tube pass through that diffraction grating or prism, and you get that spectrum. Each line in the spectrum represents a different wavelength, as you know. Spectrum is not continuous, but rather contains discrete values of wavelength. As the photon energy is emitted, will only correspond to these wavelengths. Okay? So that kind of means that you're not going to have everything. You're going to have only discrete values, because the photon energies emitted will only correspond to these wavelengths. So you have photon energies depending on each level or whatever it may be. Your photon energies will correspond only to these wavelengths depending on the metal. And this is evidence to show that electrons in atoms can only transition between discrete energy levels. If it wasn't able to if it transitioned between, like, instead of discrete but of continuous energy levels, then we would probably have a continuous line spectrum. The fact that we can only go from one energy level to another energy level through gaps, like one energy level, bam, to the next energy level, bam, to the next energy level, bam, that means that the amount of energy we lose when the electrons get de-excited, bam, 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 those are photons of different frequencies. So we're going to see different frequencies on the spectrum. Not every single frequency, but only the frequencies of the certain of the movement or of the excitation of the electrons going from one discrete energy level to another. I hope that makes sense. So to quantize it a little bit more, the difference between the two energy levels is equal to a specific photon energy emitted by a fluorescent tube. So the difference between two energy levels, we're having this and this, or this and this, or this and this. Okay, the difference between these two, okay, is equal to the specific photon energy emitted. Okay, that makes sense. If this is the difference between these two things, when it moves up or when it goes down, the energy that is lost, that's going to be equal to your photon energy. Okay, the photon energy. Let's say this is 1, this is 2, this is 3, this is the fourth shell. Okay, that's what I meant. If you didn't get that already. So it's equal to the amount of energy that the photon is emitted with, or it's the amount of specific photon energy emitted by a fluorescent tube. This is kind of, I hope you understand what this means. Fluorescent tube, and we're going back to this, this experiment that we were doing here, where you have a gas, and that gas can contain electrons, So we can quantize the amount of the amount of energy that's emitted by these gaseous particles in this fluorescent tube by finding the difference between the two energy levels. Okay, each energy level has a different amount of energy. That's your first IE and your second IE. Well, yes, I would hope so. No. Well, your first IE is going to be how much energy is needed to just take it out. Not to move it up or down energy levels. So this is going to be a tough thing to visualize for me, but whatever, just thinking of it in the form of this, because when we think of it, usually we think of this going out, the outermost already going out, but when we're thinking of something that's already inside, and we're moving it up to the next one, and then it goes back to the previous one, excites and de-excites. That's kind of hard to visualize. So this is actually something I really want to learn further. This is another, cool fact worth. I'm gonna write it. I think checking out, do that when and only when. This is important. And only when you have free time. Okay. Don't do this when you're doing studies, because that's gonna hamper your education, and you don't want that. I have experience. So absorbed in a line absorption spectrum. So this is gonna be it. That's what it looks like. And yeah, oh, thank you so much. This is so helpful. Holy shit, it is helpful. Using photon energy equations equals to HF, you can see that you can find the photon frequency by doing the following equation. Well, yes. After you find out the change, after you find out the difference, you'll get the E. And then you can put that E into the formula HF. And then you can find out the F by actually just putting that H and dividing it by both. That's cool. Yeah, that's cool. That's cool. Actually, that's actually awesome. So if you find the difference between the two and then divide it by Planck's constant, you're going to actually find the frequency of the emitted photon. Okay. So yeah. And if you can find the frequency of the emitted photon, then you know where it's going to lie on the spectrum. Correct? Guess what? That's going to be the end of this thing. And since we're going to end it off, we're going to give you a little drawing of a dude getting, you know, like this is me. Say, that's me. And I'm like running at you. I'm like running at you like this. With my electron gun. I'm like running real like weird. I don't know, dude. I don't know how to draw people. Okay, so we're gonna draw like this. That's gonna be my shoe, man. Shut the hell up, bro. God, I suck at drawing. Alright, that's me with the electron gun. You know, and I'm gonna draw my hair. It's quite long actually, so we're gonna draw it like pretty damn long, bro. Alright. And you know, I'm coming at you. You're like, ah! You know, and you didn't realize I was coming at you. Like you're just sitting on your desk, you know, watching this video. So you got the laptop open. Hell yeah. Unless you're watching on your phone, then you got your phone open as well. Hell yeah. You're just holding your phone. This is at your desk. You're just chilling. Well, not anymore, because you're about to be transmitted. So that's gonna be your shoes. All right, that's gonna be your drawing. It's gonna be your scene. That's me running in with an electron gun, and you are at the desk. You're going to be shot. Okay, so that's in about I guess you could say a 2-part series. We talked about you know, just first your basic reflection and refraction, and then later we talked about you know, your first we're gonna be holy shit, I forgot already. Kind of went through everything, so it's hard to remember, but I think the most the coolest things I remembered was probably like the wave particle, you know, duality. Oh well, the first thing we studied was very boring, but it was the polarization. This had nothing to do with anything. Well, I suppose it did. Just talks more about waves, but polarization, then wave particle duality, a little bit of how you know, electron can be proven as a particle, that kind of threw me off a bit with the wave particle thing. I thought electrons were wave particles, but no. This was only talking about photons. Oh yeah, and then the photon model and how it can be differed and why it's not the same as the wave model. And then how was the photon model discovered? You know, is light in the form of both photons and waves? Those reasons through the photoelectric effect. And then that's leading to, you know, more extra stuff where we, you know, then started shooting energy into gaseous items, and you know, the light, the photons that each of those electrons produces, putting that on a spectrum and actually finding the frequencies, finding the frequencies of each of those emissions of each of those electrons. You know, you already figured that out as well. So that's, you know, the second topic was a bit more crazy. Reflection and refraction, was there more to that, or was there really just all that there is to that? Oh, there was Snell's law, which wasn't really that interesting. But yes, okay, before we go, Snell's law, talk about it a little bit again. It's used to find out the refractive index of specific material. You know, when that N1 is going to be air, you can use that to find out the refractive index of each of those materials, find out the relationships between, you know, angles and refractive indexes and stuff. So yeah, it's gonna be it. This is what I was talking about, your little proving that your electrons can act as waves. Did I say particles in this area? My bad, that's waves, because it can diffract. And yeah, de Broglie relation was just this. I mean, I don't know, we barely talked about it. We use a formula more than actually stating what he stated, but de Broglie doesn't know jack shit, I'm telling you. Shot electron at Michael and at a baby, so that was pretty epic. And yeah, you're gonna be next. So yeah, I'll see you later.